Okay, can you all see my screen? Yeah,
Yes.
it's good to be back here, and thanks everyone for coming. And actually, this was based on joint work with Siki Lu, who's in the audience, and my advisor Prasad Raghavendra. And yeah, actually, to address what Brian said, the question mark is because we're not like 100% sure whether there are computational phase transitions, but yeah, maybe there are. Uh, so the general setup of this question is in that of statistical inference. So you have a hidden signal, which we call X, and you should think of it as being like a random n character long string, where each character is a number between 1 and q. And then you're given many observations about this string, which we call E1 through EM. And you should think of these as being like independent noisy observations. And the task is actually to recover the string X approximately. Now, actually, typically these kinds of problems tend to go through several phases. That is when you have too few samples, it's just impossible to say anything about X. But then there comes a point where you have enough samples and then it becomes information theoretically possible to, let's say, recover X better than random guessing. But the problem may still remain hard. And then finally, there comes a time when you have a lot of samples and you can actually run efficient algorithm and recover X either approximately or exactly. And actually, the theme of this talk is to try and understand the second phase transition that happens, the place where a problem goes from being hard to being easy. So with this setup in mind, let's actually jump into a few concrete questions, which we will tackle in this talk. And yeah, one thing that I want to note is actually the the predicted thresholds of when a problem jumps from being hard to being easy comes from like the statistical physics literature and community, and I guess they use certain non-rigorous but still very precise methods to make these predictions. So this talk will also spend a chunk of time going over the statistical physics-based methods. So to make things a bit more concrete, the first problem that we will consider is a problem that we call the planet Q coloring. Uh, so now the hidden signal, so you should think of there being a vertex set, which are numbered 1 through n. And then every vertex is given a uniformly random color between 1 and q. So now you have like some coloring of these n vertices. And now the samples that you receive about this hidden coloring are alpha n IID edges. They're independently identically distributed edges. But now let me tell you what the distribution of each edge is. So each sample is a uniformly random edge that straddles two color classes. So here's what I do. Of all the possible pairs of vertices, which have different colors, let's say UV, I choose one such edge uniformly at random. But I don't allow myself to choose edges which are between vertices of the same color. So for example, this edge between U and V prime is disallowed. And now the task is, once you're given this graph, you want to try and recover X approximately. And we know that this problem is information theoretically impossible when this parameter alpha, which is the density of edges, is smaller than a certain threshold, which is q times log q. And the statistical physics-based predictions will actually tell us that the point where this problem transitions from being hard to being easy happens when alpha is this simple number, which is q squared divided by 2. So now let's move on to a few more example questions, just to get a sense of the kind of model that we consider. So the next question that we're going to consider is that of like a random CSP with a planted solution. And for concreteness, let's think of like a certain specific CSP, which we'll call not all equals 3 sat. So now the hidden signal is a random plus minus one string, again on the same vertex set S. So what I do is I go through the set of all my vertices. I flip a coin and okay, this one came up plus, this one came up plus, these came minus. And then the next thing that I do is now I need the samples. So what are the samples? The samples this time are actually triples of variables. So each sample, uh, you should think of as being one of these squares. And each of these squares has an affinity to picking three variables such that not all three variables have the same sign. So for example, this clause that I've highlighted here is one where the three variables have different sign. This clause 2 is an example of such a variable. Okay, but this clause is like sort of you should think of it as a noisy sample. Like you happen to pick three variables which were of the same color, and yeah, such mistakes can happen, and these mistakes happen with probability rho. So the model we will consider will also allow some noise in the measurements. The measurements aren't perfect. And now the goal again is to actually, given just a bunch of samples of this hidden string, we want to recover this hidden signal X approximately. And now the statistical physics heuristics will tell you like a very precise picture for the values of alpha and rho for which this problem is tractable and for which it's intractable. So in this picture over here, the region that is colored blue is supposed to be the easy region, and the region which is colored white is the predicted hard region. And one thing I should mention is that during this talk, we're going to or I guess the result that we're going to try to build towards is an algorithm for solving this recovery task for a whole class of problems whenever these heuristics predict that you're in the blue colored easy region. Okay.
So Sidhanth, do you assume that the signal is random in these examples, or can they be?
Yeah, so far I've been assuming that there's a prior on the signal, and you actually know the prior. So yeah, the signal is random.
And so the guarantee will be high probability over the signal randomness too.
Yeah, I'll be over the signal randomness and also the sample randomness. The one thing I should say is you can imagine like a model where the signal is something like vertices 1 through like some number k1 are of some color, then k1 plus 1 to k2 are like a different color. And these numbers are fixed, and it's just you don't know the original numbering of vertices. And then it'll only be over the noise randomness. Did that make sense?
Yeah, thanks. Yeah.
Okay, cool.
Sidhanth, is there no impossible region? I mean, in the previous picture, you had three regions, impossible,
right.
easy.
Yeah, so like I think, for example, this problem, it'll probably have like some impossible region over here. Thing is, we actually don't precisely like know what that region looks like. So we'll just make a distinction between easy and I should say hard/impossible.
Perfect.
So see, actually predicting the impossible region is like a different game, and like there's different, again, stat physics based heuristics for that. So, but yeah, I guess in this talk we probably won't go over those. Okay, any other questions? Okay, yeah. So by the way, the reason I'm giving like many examples is just so that the ultimate model that we discuss won't seem too abstract. So actually, the point of this next model, which we're going to call planet not all equals 3 or 5 sat, is to illustrate that we're going to allow the clauses to also have multiple types. It's not like all your samples are homogeneous. You either get like sample of type 1 or type 2 or type 3 or so on. And here is a concrete example. Each sample can either be like of type not all equals 3 or not all equals 5, where not all equals 3, like we saw last time, were clauses which connected to 3 variables, which didn't all have the same sign. Not all equals 5 is the analogous thing, except a clause connects to 5 variables. And once again, there's an easy region and there's a hard/impossible region. And now for our final example, you can also imagine some kind of a model where you have some hidden signal, but actually the signal is not like 100% hidden from you. You actually maybe get some partial information about the signal. In the sense, like, so here I have like 4 different color classes, which are labeled 0, 0, 1, 0, 0, 1, and 1, 1. And I actually could possibly reveal to you the first bit of the color of every vertex. So you know which vertices are of type 0, which vertices are of type 1. And then you can imagine a model of random graph where I once again give you like alpha times n IID edges. But now an edge is either within a color class with some probability, which I'm going to call P0, or it is in a color class that has Hamming distance 1 with some different probability, which I shall call P1. And then it's between 2 diagonally opposite color classes, namely with Hamming distance 2, with some other probability P2. And even for such problems, you can come up with like a particular diagram. So here I peg the value of like P2 times alpha, and there is a very precise prediction for when it's easy to recover the labels better than random guessing. So the general model of problems that we will be studying are what we call Bayesian CSPs. And the generic setup is there's a hidden signal. And then you get a collection of alpha times n samples. And each sample you get has one of F types. So we're going to use E1 to denote like all the samples of type 1, E2 to denote all samples of type 2, and so on. And since each sample is IID, the way a sample is produced will always follow like a particular 3-step schema. So first, there is like some I which is sampled from some distribution on 1 through F. Remember, 1 through F is like the different types of samples. So the first step is you're picking the type of the sample. And now, in the second step, for each type of sample, we have a distribution which we call phi, and this is a distribution over a tuple of colors. So, for example, in the planet Q coloring question, there was only one type, and this distribution was just two random colors, C, C prime, such that C is not equal to C prime. And finally, this third step is the one where you actually pick a sample that has anything to do with n, which is like the whole instance. You pick a random tuple which matches exactly the color tuple you picked in step 2. And now the task is to recover the hidden signal X approximately. And the question is, when is this task computationally tractable? I think it's a good time for me to wait, like, say, 15 seconds to let people absorb this and also take questions if there are any.
So what you reveal here is the tuples AI?
Yeah. So the tuples AI are revealed, the colors are hidden away.
So Sidhanth, like for instance, I might say, oh, I'm going to pick a 7 tuple. and I'm going to pick, 3 reds, 2 blues, and a green or whatever.
Right.
And then I'm going to, pick a uniform sample of 3 reds, 2 blues, and a green, and then sort of connect them up. That's the
Right.
okay. Okay. Cool.
Yeah, and I guess I maybe tell you, like each tuple also comes with like one of F colors.
So except there is also ordering, right? To add to what Anupam said, there's also
Yeah,
ordering
so
among
there is
the
ordering. Ordering is allowed. Yeah. Okay, I'm gonna move on then. And yeah, okay, like I've said at least 5 times, like we're gonna go through some heuristics to predict the solution to this question. And okay, like one note that I want to make is if uh, if you're not like that familiar with CSPs, then for everything I say, the planet Q coloring problem is actually like a good problem to keep in mind. So let me remind you what this question is. You have vertex at n, each vertex is assigned a random color, and then you're given a bunch of random edges, alpha n edges, and each edge straddles color classes. And yeah, see, this is a good like canonical go-to example for everything that will be discussed. So now, I guess before we try to address the question of, I guess, how to answer a question like this, like we want to develop a theory of computational easiness or hardness. Let us look at a different theory, which comes from like study of like approximation of worst case CSPs for inspiration. And I guess this will probably inspire what we're about to talk about. So just to quickly define what a worst case contained satisfaction problem is, there's an underlying variable set x1 through xn, and then you're given, say, a list of k tuples, and along with each k tuple, you have a certain function p, which is called it's like a Boolean function, which takes q to the k to 0, 1. So for example, your tuples could look like 3 variables, and then say the function p is like the 3 sat function, or the not all equals 3 sat function, and so on. And your goal is to find an assignment to these variables x within 1 through q, so that p of those variables is the number of tuples for which p of those variables is 1 is maximized. And just to say what the punchline of this area of like maximizing the number of tuples is, so there's one algorithm. The algorithm is based on semi-definite programming, and the point is, whatever approximation ratio this algorithm achieves, whatever guarantee this achieves, we may not like be able to easily tell what it is for a given CSP, but we know this is the best approximation ratio if we assume the unique games conjecture. And I guess this was in a line of work that culminated in a paper for Arcavenda. So then this kind of motivates the question. So we said SCPs are like the best algorithm for worst case CSPs. What is the optimal algorithm for recovery and Bayesian CSPs? So it was posited by Krzyzakala and Zheborova that actually the optimal algorithm for Bayesian CSPs and similar problems is a certain algorithm which is called belief propagation. So yeah, now this is like an algorithm that I guess within TCS we don't see much, but there's a whole community of physicists who believe that like for many statistical inference problems, this is like the right algorithm, and they're completely convinced of it. So yeah, I guess there is something for computer scientists to investigate here. So now I'll leave a few seconds for questions. So now let me give like a brief overview of what the belief propagation algorithm is. I won't actually explain this algorithm, but I'll rather just tell you like some minimal amount that you would need to know. So it is an iterative algorithm, and it always maintains a certain vector, which you should think of as being a q times 2e vector, where e is like the number of edges in the graph that we got from a Bayesian CSP. So okay, let me try to make this more concrete now. So for every pair of variable L and clause R, so L is something that is in N, and R is something that is one of the observations that we made. We have an entry corresponding to the directed edge from L to R in our vector M, which is I guess the state that belief propagation maintains. And likewise for every right vertex, and for every observation that we made in every vertex in N, there's similarly an entry corresponding to the directed edge from R prime to L prime. And each entry in this vector, it's not just one number, it's a distribution on 1 through q. So yeah, for every pair of vertex and clause, there's a distribution on 1 through q. And now what belief propagation does is it starts off at some such vector m0, and then it repeatedly applies a certain update rule. So at time t plus 1, this message is, or this state, which I guess we call, these are known as messages, is actually equal to a certain deterministic update rule applied to the state at time t. So I'm not going to tell you what this update rule is, but I'm going to tell you one property of it. So the main property of this update rule is that it's a very local update rule. So for example, if you look at, let's say, the state of the vector at time t plus 1, and you index into the f to v1 entry, where I guess you should think of f as being a clause and v1 as being vertex with an n, that a time t plus 1 only depends on the state of all other incoming edges to f at time t, which I guess is articulated by this line. And very similarly, for a vertex which is on the left, which is with an n, that we call v, its message to f1 at time t plus 1 only depends on the message that it receives from all its other neighbors at time t. So I guess this is probably the extent to which I want to discuss belief propagation. But once again, I'll pause and see if.
So Sidhanth, I'm sorry, man. I did not understand.
Okay.
So
sorry. Yeah.
what are you sort of running on, and like what's happening? Can you give me a little example, or maybe something would help?
Sure. Yeah. So maybe let me just like give a very small example. So let's say you have a graph on like 2 vertices with an edge in between, and okay, this edge actually, there's going to be like some square which is indicating that there's an edge. And now let's say this vertex knows that it is red, but this vertex, it's like sort of 50-50. It thinks it's like blue with property half, red with property half. And let's say that you know that this graph came from like the planted 2 coloring model. then okay, at time 0, like okay, I told you what the distributions on these vertices are. Now, when you run one step of belief propagation, the thing that's supposed to happen is this blue vertex updates its distribution based on what it hears, and it hears from the red vertex that, oh, its neighbor is red, so it's like, okay, I better be blue. Like that's roughly what the structure of the update rule is. Okay, yeah, I think making this abstract may have been a mistake, but
That's cool. That really helps. Thank you.
okay, cool. I'll just wait like a few more seconds. Okay. Now I guess I want to say a little bit about why like there's a community of people who believe that this is the right algorithm for problems like Bayesian CSPs. So the point is, if you run so suppose the input graph you get happens to be a tree, and then you run this belief propagation algorithm for some number of steps, and this number of steps, okay, it's like the diameter of the tree, then actually the algorithm will be able to produce like a completely correct answer. So really when people make the conjecture that belief propagation is optimal for Bayesian CSPs, they're really making the leap that, oh, we know it's correct for a tree, so maybe it's also correct for graphs that look locally tree-like. And if you remember the kind of graphs we got, they were on roughly n vertices on the left, and there were roughly theta n vertices on the right, which connected to a constant number of random locations. And actually, such graphs have the property that a, a typical neighborhood, or a typical, let me say, radius or a log n neighborhood is a tree. So this is actually the intuition that guides why BP might be correct on these other graphs too.
Quick question, Sidhanth. If you have like an NA3 constraint, like in what sense is it like a tree? Like, I don't know, I'm not sure what's the graph. Like you can go back and forth and like make a little triangle.
Yeah, so actually, I guess when I say graph corresponding to a Bayesian CSP, I'm really thinking of the factor graph.
Okay.
Which is the bipartite graph you get by putting like the n variables on the left and
right,
every constraint on the right connects to.
Okay.
Also, I see something in the chat.
Oh, it was just Pravesh answering
okay.
the question. Thank you.
Yeah, thanks, Pravesh. Okay, but the issue with like belief propagation is that it's really difficult to analyze rigorously when your graph is not a tree. So actually, there is a heuristic view on when belief propagation actually works, and this heuristic view is again, I guess it was first like posited in this particular paper of Krysakala and Steparova, and we call this heuristic the stable fixed point barrier, or this method of predicting hardness, the stable fixed point barrier. And now let me try to give an overview of how this heuristic works. So the first step is you define a certain starting state for belief propagation, which does not depend on the graph at all. It only depends on the prior. And okay, like I know this is vague, so maybe in the specific example of planet Q coloring, think of the initial set of messages as being each entry of this M vector is said to be the uniform distribution on all Q colors. And then, like, okay, this is all happening as a thought experiment. So thought experiment is M0 is just said to be the set of messages which they call the trivial set of messages. And then the step 2 of the thought experiment is to try to understand what happens if you start running the belief propagation update rule. Now, there's a bunch of things that can happen. First thing that could happen is that this set of messages M0, when you apply the belief propagation update rule, it changes to a different set of messages, M1. So y of M0 actually shifts. It's not equal to M0. This is articulated by saying that M0 is not a fixed point for belief propagation. And actually, when that happens, one can show that there's a really simple combinatorial algorithm that is just based on like counting degrees, which we won't get into in this talk. And yeah, actually, such models are uninteresting for like some sort of silly reason. So we will actually focus our attention on the case when applying this update rule gave you back M0. Namely, this starting set of messages was a fixed point. Now, let's understand what happens when actually the starting set of messages happen to be a fixed point. You ran the BP update rule and you got the same set of messages back. So the thing you'd want to know is, in some sense, how stable is this fixed point? Which I'll get into what that means in a second. So, okay, since M0 itself was a fixed point, we want to understand what happens if you run belief propagation by perturbing this starting position a little bit. Like you basically run BP for like L rounds. And you want to know how like moving away from the fixed point made belief propagation behave. There's two things that can happen. The first thing that can happen is, okay, here M0 was a fixed point. You move to M0 plus epsilon. And then you start running belief propagation. And as you did that, you like slowly came back to the starting position. The second thing that can happen, and we call this the stable case. And it's stable because like M0 is a fixed point in a very robust way. But the unstable case is when M0 is fixed point in a not so robust way. That is, okay, M0 happened to be a fixed point, but like when you did a tiny random perturbation and started running belief propagation, you started like going somewhere far away. And the conjecture is actually that when you start going far away, you're actually making progress towards the real solution. And the prediction that they make is that the belief propagation algorithm actually works. Whereas in the other case where you came right back to M0, I guess, okay, I'd say like the first order prediction they make is that the belief propagation algorithm fails for most starting positions, but they actually also make like a stronger conjecture of computational hardness. But yeah, I won't like support or question this.
Can I ask another question?
Yeah, go for it.
I was under the impression that the belief propagation algorithm itself was just like, well, you just keep doing the epsilon update rule that you have. So like, it would seem that like it's obvious that like belief point or this fails if like M0 is a fixed point because the algorithm won't do anything. So is the actual algorithm something different? Like you perturb it, or?
No, but thing is, remember that like we did this thought experiment where we chose M0 to be like a very particular set of messages, which depends only on the prior. But you can imagine maybe there's some like funky algorithm which does some stuff with the graph, chooses some starting point, and then runs BP from there. But
so the question is like, does BP work is actually means, does there exist a starting point such that BP works starting from the starting point?
Yeah. I mean, at least that's what I would interpret BP working as. But
I see.
But I'm saying they make this leap that like if it doesn't work from this very particular set of messages, which depends only on the prior and not on the graph, then it.
But like it doesn't work. In some sense, it doesn't work if you like, let's say the box on the left, because formally M0 is a fixed point in that case, right? So like if you start belief propagation at M0, it'll just stay there and thereby fail.
Yeah. So that's why you try to understand what happens if you perturb it from M0 a little bit.
I see.
So I guess
like clearly there is always a starting point where things would work, right? Which is the optimal.
Which is exactly. Yeah. No. So yeah, I think that's why they try to predict computational hardness in the sense like it's hard to find the starting point.
Yeah.
But like when Lenka Zdavarova says like, I think it's an easy case, like what starting point is she starting from?
Yeah. She really means the like taking M0 and perturbing it slightly.
So you like take M0, which is like some natural thing, you perturb it slightly, and then you start BP.
Yeah.
Okay.
And okay, like thing is, for most interesting models, M0 itself will be a fixed point because okay, if you consider like planet Q coloring, any Q coloring of the graph and any random permutation of the colors will give you like valid Q colorings. So if I pick a single vertex, like it thinks it's uniform.
Right.
But the real question is like if you move it away slightly, like will it immediately bias towards a particular coloring or whether it comes right back? Yeah. Okay. I'll give people a few seconds to absorb this. Okay, I think I'll move on now. And right. So now let's actually like dig into how one can understand when when you're in the stable case and the unstable case. So the thing to do here is to say, oh, actually, if I apply the belief propagation update rule by moving away from M0 a tiny amount, I can actually approximate it with a linear function. Namely, I can approximate how much I move away from M0 with the derivative of this epsilon update rule times epsilon. And in particular, if I apply like L rounds of BP and I make like a really tiny perturbation, I expect to land at M0 plus this derivative matrix, whole thing raised to the power L times epsilon. So really the point is, whenever this b to the L times epsilon vector goes to 0, we expect that be in the stable case. And we also expect that this b to the L times epsilon vector just becomes something that's much larger than the magnitude of epsilon when you're in the unstable case, as you make L very large. But actually, since B is linear, what I said here is kind of saying exactly the same thing as actually in the stable case, because you did random perturbation, you went back to 0. It's probably the case that all your eigenvalues are less than 1. So multiplying B with epsilon L times actually shrunk it all the way back to M0 itself. But if B happened to have some eigenvalue that was greater than 1, now since epsilon is pointing in a random direction, epsilon probably like correlates with this top eigenvector of B some amount, and actually multiplying epsilon with b to the power L really highlights this eigenvector. Now, this suggests a natural algorithm, which is if you want to move in a direction which actually correlates with the hidden signal, I should actually compute what this matrix B is and output its top eigenvector. And yeah, I should say that this algorithm was proposed by Krzyzakala, Moore, Mosul, Neiman, Sly, Zdevorova, Zhang in the context of like the stochastic block model, or for this community detection problem in the stochastic block model. And eventually it was proved that for community detection, this essentially works. And it's due to Bourdnov, Lelarge, Massolier. And our work can be seen as like an extension of this to problems beyond stochastic block model and community detection, namely to all Bayesian CSPs, like I mentioned. But yeah, once again, I'll have like a short question break. Okay. But now I want to get into. So okay, I told you that like whether you're stable or unstable kind of depends on the eigenvalues of this B matrix. But even the eigenvalues of the B matrix could be like a difficult thing to analyze at first. So I'm going to spend some time talking about how one predicts whether B has large eigenvalues, namely one's greater than 1, or whether all its eigenvalues are less than 1. And towards doing so, let me remind you of like one key feature of this BP update rule, namely this Y function. It's like a very local function, and the message that a vertex sends to another vertex only depends on its incoming messages from all its other neighbors. So now, in order to understand what happens when you run L rounds of belief propagation, let's pick a random vertex in our graph, which we shall call V. Now, because of the nature of this belief propagation update rule, if I look at its radius L neighborhood, which by the way is most likely going to look like a tree, all the influence on this vertex happens due to vertices which are some distance L away. So it's only this set of leaves which influence what happens at the root vertex B. So the question is, how does the perturbation at the leaves influence the perturbation at the root? And actually, towards understanding this, the thing that we really want to know is what is the derivative of the perturbation at the root with respect to the perturbation that happened at the leaves. And actually, now the perturbation at the root, because we're making the perturbation of the leaves like really small magnitude, is something like the following. You take a sum over all leaves, namely you enumerate every leaf over here, and then you look at the path that a given leaf has to the root, and then you ask, what is the derivative of the root with respect to this particular leaf? It's going to be some number which depends on what's in this path. Oh, it's not going to be a number. It's going to be a matrix that depends on what's in this path. And actually, I made a mistake in the description of this matrix. That's embarrassing. So the matrix is actually the following easy to describe matrix. it's a Q by Q matrix. So let's like focus our attention on one leaf S. What you get here is a Q by Q matrix, and the C comma C prime entry encodes some notion of how much does knowing that the leaf S has color C prime influence the probability that the root V has color C. So in particular, it's this conditional probability minus just the probability without any conditioning. So this is like some kind of influence matrix, and is what guides the magnitude of the perturbation. And if you do a short calculation on what the expected norm of the perturbation of the leaf is, sorry, of the root is, and normalize it by the magnitude of the perturbation at the leaves, you get something that looks like you take a sum over all leaves, and for each leaf, you have some notion okay, really, you should think of this as being like correlation between color V and color S. And the precise notion of correlation is given by the square of the Frobenius norm of this like particular influence matrix. And now the thing that we want to understand is whether this particular notion of correlation decays, namely it goes to 0, or if it blows up. And actually, we say we're in the stable case if this particular notion of correlation exhibits decay, and we say we're in the unstable case, this particular notion of correlation blows up. And yeah, I guess the nice thing about this is for any Bayesian CSP, if you tell me what the parameters are, I can write to you like a constant size matrix L, and just based on whether all the eigenvalues of L are less than 1 or greater than 1, you know whether you're in the stable case or in the unstable case. So this is like an easily determinable condition too. Okay. Any questions about this? Okay, so I just want to iterate that the punchline of like this part is isn't saying that you're stable when there's correlation decay, and you're unstable if there is no correlation blow up. And okay, I did like hint at what our result was, but I think now I can like state it formally. So actually, given an instance of Bayesian CSP, there's an efficient spectral algorithm which can actually recover the hidden signal better than random guess would. Whenever you're in the unstable regime, whenever this correlation blow up happens. And okay, I wanted to say a couple of things about how to analyze this algorithm, but seeing that I have only 4 minutes left, I think I first want to talk about like 2 open questions. So, okay, but before I do that, I first want to see if the audience has questions.
So maybe you already answered this, but this is a quick question. When the conjecture is that BP works, does it mean that you beat random, or does it mean that you recover the vector exactly? Like, what does it mean by?
It means you beat random guessing.
Okay. Okay, so then essentially this is a proof. I mean, it's not maybe a proof of BP itself, but it's a proof that
it's not proof of BP itself, but but it's like there's a prediction that okay, so they're like it should be algorithmically easy, and they're like we can give you an algorithm, it's BP, and we're saying okay, like we can give an algorithm whenever you predict there's an algorithm. Though our algorithm it's inspired by BP, it's not BP. It's basically based on like using the eigenvectors of this derivative matrix in some like sort of strange way.
And do you suspect there is a reason why there is a reason for the hardness of exact recovery of the planted vector, planted assignment?
Yeah, so actually, like in these regimes, exact recovery is also maybe information theoretically impossible for a lot of these problems. Like one simple reason is if you're working with a very sparse graph, like there's going to be some vertices in N which you don't receive any measurements of, like none of the clauses actually connect to them. Then you can't really say what they were. But okay, you could ask like, what is there an algorithm that can like recover exactly on the rest? But I still think the answer is no, but maybe for more complicated reasons.
And one final question. There is, I guess, a difference between solving the CSP and recovering the planted assignment.
Yeah.
Always possible. Or at least there is nothing information theoretic barring, like there is no information theoretic barrier for it, right?
Yeah. So yeah, actually, you bring a good point, because here it's all about like recovering what was hidden. And actually, for example, for this planted not all equals 3 sat, so okay, let me maybe I should actually like highlight this, since it's somewhat interesting phenomena. So okay, if you look at like this plot, so let's say you're planting a not all equals 3 sat, so you're planning a hidden solution in a not all equals 3 sat formula, then actually here 4.5 is the degree when beating random guessing is possible. But I think 4.5 is actually smaller than the satisfiability threshold for completely random not all equals 3 sat instances. So I think maybe if you take completely random not all equals 3 sat instance at some density higher than 4.5, maybe like, actually Ryan might know the number better, but
Sorry, you know, it's higher. It's like 7 or so. It's
right.
or well, no, don't call me on that. Never mind.
Yeah, I'm actually also not completely sure.
I remember 6 from your paper, but okay.
Yeah, no, what I was gonna say is you can, yeah, so somehow you can like recover the planet solution better than random guessing, even when there are other satisfying assignments. So this is like really using something about how the hidden signal like changes the instance.
Even below the SAT threshold, you're saying, even
Yeah.
intrinsically whatever, like even when the instance is intrinsically satisfiable or has lots of satisfying assignments, you're saying somehow the instance is changed enough so that I can recover some non-trivial information about the planted assignment. So in particular, the planted
Yeah.
distribution even below the SAT threshold is noticeably different from the random NAE SAT.
Yeah. And actually, I can give like a reason for this. So the reason is the following: like when you're say sampling like planted random NAESAT, an instance I is sampled with probability proportional to the number of satisfying assignments it has. So it's not going to be like a uniformly random instance in some number of clauses. It's going to be biased towards instances which have lots of satisfying assignments. So that's why like they become easy to notice and they stick out in some way. And yeah, actually, there's like some further conjectures that when you're doing this, whenever you have like an abnormally large number of satisfying assignments, the reason you have that is because there's a big cluster around like the planted satisfying assignment, and that's why that spectrally sticks out. But okay, maybe I can move on to the open questions part. So yeah, I think I'd say like one pretty mysterious thing is, okay, they predict that BP fails, but they actually also say that this is when hardness starts to happen. And one question is, can you get any kind of intractability evidence? Like, for example, it'd be good to say that like low degree polynomials fail, or like some strong SDPs also fail. But actually, another interesting question is like some reduction based hardness. Like here, if you look at all these Bayesian CSPs, there's always like some easy region and there's some hard region. And one concrete question with respect to reductions is, let's say you assume hardness somewhere in the hard region, not necessarily like you don't assume the whole region, you only assume like it's hard at some particular point. Can you, via reductions, show that this implies that it's hard everywhere in this like red colored region? Yeah, this is the main reduction space question. The second one is actually the algorithm that we gave beats random guessing, but these people actually also have like precise predictions as to what the optimal fraction of verses whose labels you can correctly recover is. And again, it's based on some heuristic analyses of belief propagation. And actually, even for the simplest Bayesian CSPs, it's not known how to efficiently recover like this optimal fraction. So yeah, I would say just drawing like an analog in the worst case setting, beating random guessing is kind of like asking when is a CSP not approximation resistant, but this is kind of asking what is the optimal approximability that you can hope for, and that question is not answered by us. Okay, I think I'm 5 minutes over time, so I'll be around for more questions and discussion. And thanks everyone for coming. It's nice.
Thanks, Sidhanth. Great talk.
Oh, yeah, thank
Can
you,
I ask
Ryan.
you a small question? It's probably
Yeah,
like against the whole spirit of like BP and so forth, but it's like a little bit like annoying that like in the instances, like there's two types of vertices, like the constraints and the variables, if you will. I mean, is there any way to set it up so that there's only one type? Like given that like this, this Bayesian CSP framework you have is pretty broad, like can you cook it up in such a way that like there's only one type of object, and like so that you really just have like a generic graph that BP runs on rather than a bipartite graph?
Yeah, okay, one thing is actually, at least when we were like analyzing all the spectral algorithms and stuff, the kind of graphs that we got were like we only worked with n vertex graphs instead of like full n plus like number of constraints number, and it was like by, yeah, I guess as I'm saying it, you probably know what I'm talking about, but I'm just gonna like keep saying it for everyone's benefit. So for every, let's say you have like a factor node which connects to k variable nodes, you can imagine like putting a k clique on these variable nodes and then putting like some appropriate matrix weights on the edges. And this is the graph whose properties we study.
So then it's not a tree anymore.
But it's not a tree anymore. So yeah, that's a bit annoying. So yeah, like even when you're running belief propagation, you kind of need to remember who belong to the same clause and who don't.
Okay.
Okay, you can do all the BP update rules only on variables, but a variable does need to know which neighbors of it belong to which clause. It needs to be able to classify all these variables as being part of the same clause.
So I guess I have maybe a somewhat fluffy question, but let me put it there anyway. So all of this is about random instances, right? Like where the clause structure or whatever, like the factor graph is random, and the literal pattern on the CSPs is in some sense random, or at least I mean, you have this particular distribution to sample them, right? Is there any sense that this BP machinery, etc., is like more general, or is it like really tied down to basically this particular choice of the random model? Like how, like I guess okay. I mean, if you're sold on this model being super duper important for whatever reasons, then yeah, okay, that's great. But let's say that you are a computer scientist and not a stat physicist, so you don't think of them as like spin glasses or whatever. You really think of them as, well, one particular distribution of CSP instances, and I care about several. So what, like, are these like algorithms transferable? Like, do we have an idea of what properties of the distributions are really important here?
Yeah, no, that's a really good question. Yeah, so okay, I'd say these algorithms work for like, you can probably like cook up many random models for which these algorithms would work. There's a bunch of work on like analyzing BP on arbitrary but locally tree-like graphs, which I guess is some form of like transferability.
Yeah, so I guess it would mean that maybe if things are deregular expanders or something, then things would also work. Doesn't need to be a random graph or something. Is that like the right take?
Oh yeah. I think at least yeah, for a lot of questions, like maybe the graph structure isn't that important. Like for CSPs, okay, yeah, let's take like CSPs for example. Okay, I haven't like gone through the full analysis and all, but I think the graph structure isn't important. It's just important that like your negation patterns are random, and maybe your graph is an expander and has like somewhat high girth, or maybe not even girth, like some bicycle freeness property, like no two short cycles are closed.
Okay, and you think that all these precise threshold predictions also would work for general models?
Yeah, I think so. For if you are assuming that your graph has some pseudo-random properties.
Cool. That's very cool. Yeah, that's very cool. I'm a bit surprised that the numbers don't change, but I guess they don't somehow.
Well, the numbers would depend on the model that you're using. But I'm saying you will be able to get numbers.
I see.
Well, okay, actually the numbers only depend on like this particular thing that I was mentioning with like you look at a tree, you look at this particular problem on the tree, and you try to understand whether there's like correlation decay if you go L levels down.
So, but if your L local neighborhood is like locally tree-like, then it
Right.
seems like the numbers would be exactly the same.
So it depends on what the distribution of the tree is too. So for example, these numbers would differ slightly between like, say, a tree where each vertex gets a random number of like children versus if it's like a regular tree. But they're only slightly different. So it's more so like a deregular tree, like every vertex has d minus 1 children. But then in one of these, like, or if you have Poisson d children, each vertex has like typically d children. So that's the growth rate of the latter is slightly higher.
I see. But basically, okay. So but that really solves, I guess, the question I was asking. Like somehow these things are general. You need like some basic combinatorial property. Local combinatorics of the graph is somehow all that is important apparently.
If you have like say random signings or something like that.